Let's continue our analysis of our non-homogeneous terms and what our form for a particular solution might look like. So here again, I have a second order differential equation. I have a non-homogeneous one, good constant coefficients. Let's pull the same game. Solve the corresponding homogeneous equation. Tell me what the particular solution's form should be. What's the thing I have to do first? So I have to solve the homogeneous one. So in that case, in this case, that's the expression y double prime plus y equals 0. The auxiliary equation that goes with that is which gives me plus or minus I, complex roots, which means my homogeneous solution part, yc, is C1 times what? Right. C1 cosine x and C2 sine x. Now here's my problem part. My first reaction is great. Look at the non-homogeneous equation, and then we have yp, right? Wait a minute. Sine x. Sine x. Even though there's an x multiplied by it, that's still considered a repeated term. So what should I have for yp? If I've got a sine x here and an x sine x here, what do I need? I'm going to need an x squared sine x. And if I have an x squared, I might also need an x. I might also need a constant because I'm going to take two derivatives. So when I think of yp, I need x squared sine x. And that means I need a quadratic term, ax squared plus bx plus c times sine x. Because it might not just be an x squared, and it's multiplied because in g of x, it's x times sine of x, not x plus. If we just add it, I just add on. But they're multiplied, so I got to multiply together. But sine never shows up alone. What always shows up when I see a sine? Yeah, they're going to come in pairs. Sine's going to come with cosine because I'm going to take derivatives. Derivative of sine is cosine. So there's going to be another cosine term. But that has to be multiplied also. And here's the problem part. I don't know whether I'll have the same coefficients on the sine term that I have on the cosine term. So really, there could be a whole different quadratic piece times the cosine of x. which unfortunately means if I actually wanted to solve this, I'm going to have to take two derivatives and set that equal and gather all my like terms. And that means the product rule twice for each derivative. Oh boy. There's a lot of algebra from here on down. And unfortunately, a bit of Calc 1 derivatives out the wazoo because I got to do product rule and then gather and then do product rule again. Just ugliness. And then I'll end up with 6 variables to solve for. Fortunately for me, this right-hand side is just something x sine x. All the other ones will be 0. So whatever x squared sine x coefficient I have, that's going to be equal to 0. Whatever cosine times x squared coefficient I have, that's going to be 0. A lot of these should just end up being 0. It's going to take quite a bit of work to get there from here, though. And that's the downside to this method. In spite of the fact that it works, it's a lot of algebra. And I mean a lot of algebra. It doesn't only work for quadratics. Here's a non-homogeneous equation. Only this one's order 3. Big deal. Same exact process. Solve the corresponding homogeneous one, and let's figure out what our particular solution's form is. So the corresponding homogeneous equation is going to get an auxiliary equation. Y triple prime minus 6y double prime equals 0 becomes r cubed minus 6r squared equals 0. Which gives me and oh, wait a second. Right. But r equals 0 is in there twice. Because when I factor this, it's r squared times r minus 6. So the r in there is twice. So what's my homogeneous solution look like? YC. Because it's e to the 0x. E to the 0x is just 1, but it's repeated, so I get 1 and then I get an x times a 1. And that's these two pieces. Now, what's my particular solution going to look like? Part of this is easy, part of this takes a little more thought. Hit me, man. Almost. Whenever I see the cosine, I'm going to get a sine. So I'm very happy to say, yes, there's a cosine x, there's a sine x. But that constant you gave me, a, isn't that already here? So I should add an x, right? But that's already here, which means I need to add another x. I should get an x squared, right? If I get an x squared, I get all the other stuff to go with it. But I'm pretty sure that even if I write ax squared plus bx plus c, these two pieces are going to get swallowed up at some point in these two pieces. So I'm pretty sure those are going to end up going to be 0. And then I'll get cosine of x and sine of x. And I don't care which order you put those in. Even if I have initial values, once I have an initial value problem, I can use those, solve for C1, C2, C3, or whatever setup I've got. But understand, this means I'm doing a bunch of derivatives and a bunch of algebra to get these values. Here we go. I want to do this one all the way through. I want to solve this one. I want the corresponding homogeneous. I want the particular, and then I want to find the numbers. Let's do the whole thing. My little brother was a theater student. So I hear him, okay, people, let's take it from the top. The first thing we create is right. The auxiliary equation goes, though, with the homogeneous version. So I need to write that down to make the auxiliary equation. So I get rid of this part. 5y double prime plus y prime equals 0. What's my auxiliary equation then, Code? So I factor out the r. I get 5r plus 1. And that gives me r equals 0 and r equals minus a fifth. So what does my homogeneous corresponding solution look like? The complementary solution. YC. C1 plus C2. The downside to this is that I cannot solve for the C1 and C2 yet. I don't have the complete solution. I can't solve until after I've got the complete solution, which means I need the particular solution version to go forward. What should YP look like? Okay. So what did you said you got stopped there.
Yeah,
Talk to me about it.
Cause it equals -6x.
Right?
So I know when it's 3 minus cosine, you get cosine sine x, so I was just kind of confused where we left off, what's it?
Okay, well, if it's a 6x, I should get like ax plus b, right?
Okay.
I should. So my first reaction is, shouldn't it be ax plus b? Except that duplicates this, doesn't it? And that x duplicates this. All right, wait a minute. That's a problem. So I really, since this would duplicate, I need an extra x. Really, I should do ax squared plus bx. I could also do a plus c. But that plus c would get sucked up into the c1, wouldn't it? Just like I mentioned up there, that the bx plus c would get sucked up because there was an x and a constant in the corresponding solution up there. So these two pieces would get sucked up into here. A plus c would get sucked up into there. I really don't need it. So I'm going to use this instead. Let's see if we can find a and b now. What do I need to do? Yp prime, yp double prime. In the couple of sentences I know. Was vergessen Sie ihr? What do you get here? Put those back in our non-homogeneous differential equation, and we get 5y double prime plus y prime equals -6x. Okay, the only x term is here. So 2a must equal -6. These are the constants. So I get 10a plus b must be equal to 0, because there's no constant on that side. Oh, wait a minute. This top one gives me a equals -3. That means -30 plus b equals 0. I know b. Perfect. Wonderful, marvelous. Yp is -3x squared plus 30x, which means I know my overall solution. My overall solution, yc plus yp, is c1 plus c2e to the -1/5 x minus 3x squared plus 30x. Now I can use my initial conditions. All right, my initial condition, the first one, said y of 0 equals 0. What happens when you plug in 0 up there? That's a constant. That's e to the 0. That's a 1. That's 0. So I get c1 plus c2. I don't have either value yet. The other initial condition was, but that means I need y prime. So before I can do that initial condition, I need y prime. Where is c1? C2, 1, okay, that's going to be -1/5 C2 e to the minus 1/5 x minus 6x plus 30. Now I can plug in y prime of 0 equals 10. What was the value? Negative 10. So I get minus 1/5 C2. That's a 0 plus 30. I can solve for TC2, then I can go back and solve for C1. So this says, move that over, 1/5 C2 equals 40. C2 is 200. What's C1? There you go. And now you solve the equation. All the way through, you know exactly what our solution looks like. Y equals minus 200 plus 200 e to the negative 1/5 x minus 3x squared plus 30x. This is section 4. Section 5 does this a different way called the method of annihilators. The method of annihilators is a functional analyst's wet dream, and that's why Burns loves it so much, because that's his primary field of study. He really did, it's the same thing from a different perspective. It makes me crazy. I'm just kidding. If you really want to, feel free to read through it. I will gladly talk to you about how it's worked out. But I think there's a better way. And the better way doesn't require me to guess. So I'm going to trade my guessing and taking derivatives for integrating. I'm going to go back to my previous idea. Not quite reduction of order, but it's related. I'm going to think about integrating factors. This method is called the method of variation of parameter. And really it is, let's work with our integrating factor. When I had y prime plus p times p of x times y, all right, I got to write that again, y prime plus p of x times y equals some function, we let our integrating factor be e to the integral of p of x dx. But I'm doing second order differential equations. I'm doing higher order differential equations. Let's just think about second order for a minute. There's my second order differential equation. Let's mess with it. Because this one, this first order differential equation is in standard form. It's got the highest derivative isolated. I've got an a2 of x. Let's divide that away. If I divide by a2 of x, then I'm going to get y double prime plus something, y prime, I'll use p again, plus something else, all right, capital Q, y is some other function. I think I wrote this backwards. All right, wait a second. Up here, change this f, change that to a g, because remember in our non-homogeneous equations, we were using g of x. Change that to a g. When I divide, we'll call it f of x. I didn't want to screw up the rest of my 4 pages of notes. Sorry about that. That should be g, that's f. Now, here's the best part. If p and q are constants, I'm done. Solve the quadratic equation, walk away, right? If p and q are numbers, that's what we were just doing. And my solution would look like something else. The corresponding homogeneous part would look like this. And C1 and C2 are just numbers. We're using the superposition principle here. All right. This is as far as I can go without saying, what the do I do with this? And I say to myself, wait a second. When we were dealing with reduction of order, I had one solution. And instead of multiplying it by a number, multiply it by a function. I changed a number to a function. These two are parameters. They're numbers that we can find. The method is called variation of parameters. Let's change C1 and C2 to functions. Let's let our parameters be variable. All right, in my variation of, in my reduction of order, I called it U, right? U of X, but now I've got two of them, so it'll be U1 and U2. The next two steps suck. Take the first and second derivatives of that. Remember what our differential equation looks like. I'm going to put a little star right here so we remember to come back to that because the goal is to solve that equation. Fine. All right, here we go. The first derivative, y prime. Product rule twice. U1 prime, y1 plus u1 y1 prime, u2 prime y2 plus u2 y2 prime. Not so bad. The second derivative is now the product rule 4 times. But when I do the second derivative here, I get u1 double prime y1, and then I get u1 prime y1 prime. When I do the second derivative here, when I do the derivative here, what's the first thing that comes out of my product rule? Isn't that the same thing? So I get 2 of these. Oh, that was nicer. And then I get u1 y1 double prime. The same thing's going to happen with the other pair. I'm going to get u2 double prime y2, and then I'm going to get 2 u2 prime y2 prime, and then I'm going to get u2 y2 double prime. Oh, Lord. All right, I did say the next 2 steps sucked, and that was step 1. Here's step 2. Take this y prime, and y double prime, and plug it in there. Okay. Y double prime plus P times Y plus Q times, P times Y prime plus Q times Y. All right, no. We can do this. We can do this. U1 double prime Y1 plus 2u1 prime Y1 prime plus U, if I can write right, U1 Y1 double prime plus U2 double prime Y2 plus 2 U2 prime Y2 prime plus U2 Y2 double prime. Good Lord. Plus, all right, wait a minute. It's P times U1 prime Y1, right? It's P times Y prime. So here's Y prime. Let's line up. This is a U1 prime Y1. I'm going to put it here. U1 prime Y1. There's U1 prime. I'm going to put it right here. P U1 prime Y1. Is that where I want that? And then P times U1 Y1 prime. And then P times U2 prime Y2, and then P times U2 Y2 prime. I'm not sure stuff is lined up the right way. We'll screw it. We'll deal with it later. Q's. Q has a U1 Y1. Oh, right, because it's just Q times Y. Q times U1 Y1 and Q times U2 Y2. There, it did line up. What do you mean it lined up? Well, let's take a look at this for a second. This group of 3 right here and this group of 3 right here. This first box. What's in that box? Oh, hang on a second. This box right here, U1, Y1 double prime plus PU1, Y1 prime plus QU1, Y1. That's just what's in that first box. Everything's got a U1 in it, right? Factor that out. Hang on a bloody second. Where did Y1 come from? Back when I was working this out, I said Y1 came from what? Y1 came from thin air. I made it up. No, it came out of something. And YC is the solution to what? What's the C stand for in YC? Unfortunately, no. C1 and C2 stand for constants, but it's Y sub C. What's that C stand for? And the corresponding homogeneous solution. That means Y1 is a solution to the homogeneous equation. This homogeneous equation, homogeneous means it's equal to 0. That whole thing is equal to 0. Boop. Slid off the bottom of the page there. Guess what's in the second box? Because that's going to be U2 times Y2 double prime plus PY2 prime plus QY2. It's the same exact setup. This box, U2 Y2 double prime plus PU2 Y2 prime plus QU2 Y2 is U2 times 0. Holy moly, a bunch of this stuff just got thrown out. 6 terms out of 12. I just cut my workload in half, which I'm pretty happy about, personally. So let's look at what's left. What's left? Equals U1 double prime Y1 plus 2U1 prime Y1 prime plus P U1 prime Y1. And then the same stuff in Y2 right here. Plus U2 double prime Y2, 2U2 prime Y2 prime plus P U2 prime Y2. Um, um, double prime times y, prime times prime. That looks like it should be the product rule. Except there are two of them, right? Let's split it back up. I'm going to write this again. I'm just going to write two copies. So I'm going to write u1 double prime y1 plus u1 prime y1 prime plus another u1 prime y1 prime, and then p u1 prime y1. These are going to get grouped together. Same thing for y2 and u2. If, here's the big if. The big if in all of this is this is a product rule derivative. So is this. But this is supposed to be the particular solution part. This is supposed to be yp. So when all is said and done, this should be equal to f of x. Mother. Okay. The thing inside the parentheses right here. I said that looked like a product rule. What is it the derivative of? That's the derivative of u1 prime times y. And this one down here is the derivative of u2 prime times y2. That should be a y1, not just a y. u2 prime, y2 prime. Okay, hang on a second. u1 prime y1 plus u2 prime y2 all prime. That's those two things added together. Plus p times u1 prime y1, u2 prime y2. Holy crap, that's the same thing. Plus u1 prime y1 prime, u2 prime y2 prime. One of two things would make this ideal. If one of these terms was a constant, then its derivative would be zero, right? So if one of these was zero, it would disappear in two places. If this was zero. But this is supposed to be equal to f of x. hang on. I can really turn this into simultaneous equations. There's simultaneous equations that involve derivatives, but they're still simultaneous equations. U1, Y1, there's a prime here, plus U2 prime Y2 equals 0, and U1 prime Y1 prime plus U2 prime Y2 prime equals f of x. If this thing were 0, it would cancel out in both of those places, and this would be f of x. Oh my God, look at the giant pile of garbage this has given me. I have not done so much algebra in one sitting in weeks. But I have simultaneous equations involving functions and their derivatives. I'm going to steal a trick from class I know you all took. Let's go back to linear. How do I solve simultaneous equations? Y1 and Y2, Y1 prime, Y2 prime. Isn't that a setup for a Wronskian? Okay. Kramer's rule for solving systems of equations with determinants is going to save me here. Here's my Wronskian. The Wronskian of Y1 and Y2. If I think of the Y1 and the Y2, then the coefficients of my equations get replaced by the column made out of the other side. So I need two other matrices. I'm going to call them W1 and W2. In W1, we replace the first column with a 0 and an f of x. And in W2, we replace the second column. Kramer's rule tells me that U1 prime is W1 over W, and U2 prime is W2 over W. That's U1 prime and U2 prime. I can now get U1 and U2. I can integrate and get U1 and U2. Son of a, it works! People, I don't know who was smoking what when they came up with this. This is the longest, weirdest thing I've seen. And look at what we combined. I combined my integrating factor with my idea of varying parameters, which is what gave me the integrating factor in the first place from reduction of order. This, holy crap. All right. It's kind of shell-shocking at the moment. And I am 100% going to tell you up front, I hate going through this procedure over and over and over. I'm not gonna. Those things tell me exactly what I need to know. This is the whole process. This set of 5 formulas right here. Put a box around it, put a star next to it. We're going to do one on Monday. From start to finish. But I couldn't just give you the formula and say, here, believe me. Because I could be full of shit. I had to show you where they come from. Somebody had a brilliant idea. I wanted you to see. But we'll do it on Monday, so take the weekend and recover from the blast of algebra that's just thrown your brain out the back door. I'll see you all on Monday.